So we are dealing with the 14th problem in this series. This is problem number 3.14. The problem is stating a very long, straight, uniformly charged thread carries a charge lambda per unit length. Find the magnitude and the direction of the electric field at strength at a point which is at a distance y from the thread and lies on the perpendicular passing through one of the thread's end. So if we start this problem, the first thing that we need to understand is again the diagrammatic aspect of the problem. So this is what the problem is talking about. So we have a large thread of charge. It extends up to infinity. It is having a charge spread uniformly over it, and this is referred as lambda. And through one of its end, at a distance y, we are asked to calculate the value of electric field. So in order to start this problem, we consider at a distance x an elemental patch of length dx which is having charge dq. So now this patch subtends an angle theta at this point. So this patch subtends an angle theta at this point. So at an angle theta, it subtends an angle d theta at this point, and it will create an electric field dE. The two component being dE cos theta and dE sin theta respectively. So if we write the expression for dE, so we will be calculating the two aspects of the problem. We will be calculating along x-axis. So along x-axis we say Ex is equal to integration of dE cos theta. dE can be written as k, dq can be written as lambda dx by x square plus y square, and then this cos theta term that we have. So this is the value of Ex, or electric field in the x direction, which we have. Now the next thing that we do is we use substitution. So for substitution we are using tan theta as x by y. So x can be written as y tan theta. So dx can be written as y sec square theta d theta. And therefore in the x-axis direction we can write the expression as k lambda integration of cos theta dx can be written as y sec square theta d theta upon x is y tan theta, so y square tan square theta plus y square. So 1 plus tan square theta is sec square theta. And if we talk in terms of angle, then the angle at the base is going to be 0 degree, and at the farther end it is going to be 90 degrees. So the angle subtends from 0 to 90 degree. So this is the expression that we have, and we are left with k lambda by y integration of cos theta d theta 0 to 90 degree, and this one turns out to be k lambda by r, or lambda upon 4 pi epsilon naught y that we have. Now we need to solve in similar way. So similarly, if we solve for Ey, so Ey is equal to dE, and this time we have sin theta component. So if we look properly, all the values of the integral remains the same. The only thing that happens is that we write sin theta over here d theta 0 to 90 degree. And on solving this one also, we get the magnitude for dy as lambda upon 4 pi epsilon naught y. So one thing that we understand from here is that the magnitude of Ex and Ey is same. The magnitude of Ex and Ey is same. And both the magnitudes are being equal to lambda upon 4 pi epsilon naught y. And therefore the problem is asking us to calculate the net value. So therefore E net can be written as Ex square plus Ey square root. So we get root 2 lambda upon 4 pi epsilon naught y. So this is the answer to the problem that we have, problem number 3.14. So we calculate the value of E along x-axis, E along y-axis, and then we calculate the net value of electric field. And since both of them, that is Ex and Ey, are equal in magnitude, so it is directed at 45-degree angle from the thread. So this angle Ex and Ey is same, so we say it is directed at 45-degree angle from the thread.